Okay, everyone, please pay attention to the slides. So yeah, we will start today's discussion on the chapter 5 of our that textbook, and it's week 11. So today we'll continue to talk about the OO design. How can you make good design, which we talked several weeks ago. Like, what should we meet? What kind of criteria is a good design? It's make a design a good design. So first, let's review a little bit. First,
it does what the customer wants to do.
Yeah. First thing first, it does what the customer want it to do, right? Otherwise, it's nothing. It's that. You mean it's beautiful software? Well, it does something else other than the customer needs. No one's gonna pay for that. It's a wasting of time. Maybe you enjoy that process, but still, you won't enjoy it for too long. Right? Okay. How about the second?
Second is use object-oriented.
Yes, principles. The most important thing here is it does, well, every class does what it's supposed to do as a class. Like not a computer class. No, sorry. Maybe you have a class of glasses. Well, it shouldn't have the functionality of the clock, right? Something like that. If you do want sunglass have a function of clock, maybe it's some special sunglasses. Well, you need to use that has a relation. Compensation. Okay, compensation. We'll talk more about compensation and this inheritance in this chapter as well. Okay, how about the third one? Yes, extendable. Extendable, make it easy to maintain, something like this. Changeable. Alright, so this is quite abstract. How can we decide how can we make a software changeable? Something like that. Well, still, we refer something to the object-oriented design principles there. Alright, if you really like following these principles, it make it easier to change. But another important thing is what we're going to talk about today. How can we design, like plan for all these changes? Okay, plan for all these changes. How can we make our design more flexible to adapt future changes? Okay, so that's what we will talk. All right, change. Oh, let me double check if I'm on live. Yes, change. So the one constant in software development is change, right? It changes a lot of times. Well, especially today, it's not like decades ago. You have a design in the beginning. You have a waterfall model. Okay, most of the time we're not doing waterfall anymore. It's iteration by iteration, like agile model, which is most popular thing. And take out your cell phone, check how many updates are there. You need to update in the App Store, in the Android store. Okay, change. We have to. So take example of the guitar search application. Okay. Well, when we are specifying that example, we actually did a lot of changes. Like, we want different types of guitar, and like guitar has different number of strings, maybe. Okay, so we want to adapt to those changes, and we made that in the previous design. But now we're thinking about more changes. Like here, we want to sell the mandolins too. Like, the guitar shop is no longer a guitar shop anymore. It sells all kinds of instruments. Okay, mandolins too, other things. Okay, I have to click here. Yep. So, yeah, this is original stuff. Like we have an inventory system with a guitar, and we put things into the guitar specification. Okay, if you still remember the guitar specification, why do we have it there? It's because we are thinking about, okay, we are searching for the guitar using a guitar object, but that's actually we just search for that with the specification of guitar. Then we put guitar specification as a separate class there to do that for us. Yeah, on that purpose. And then we use guitar specification for the search instead of using the guitar. And guitar specification is actually an attribute of guitar. Right? Remember this association? This means guitar has a reference to guitar specification, which means guitar specification is an attribute of it. And guitar specification have all this builder information type wood. That's the original design. Yep. Now some new requirements is coming. Rick is gonna make more profit by selling all types of instruments. Maybe now we're adding something like mandolins. So to aid support for mandolins, create a new abstract base class called instrument. So that's what we're doing right now. Okay, if we want to do like more instrument, right? So this is like some of the programmers are doing right now. Okay, because we want mandolins. So right in the designer's mind is we create an abstract class called instrument with mandolins and guitar as subclasses. Right? Sounds reasonable, is it? Because guitar and mandolin are all instruments, right? So makes sense. And abstract classes define behavior, and subclasses implement that behavior. Right? Makes sense? Yes. And mandolin specification, because that's similar to the guitar specification. So similar. Yeah. So what we do is we create another abstract class called instrument specification with guitar specification and mandolin specification as subclasses, right? So that yeah, we will see the class diagram here. Alright, this is inventory, which has this instrument and guitar and mandolin are subclasses of instrument. This is okay. This part is okay. Alright, so this is actually a page at the right side of this first page. Okay, so this instrument specification is actually connect to here the instrument. Alright, like what they use association, aggregation. Like instrument has instrument specification. Okay, and instrument specification has different subclasses. One is called guitar specification. One is called the mandolin specification. Okay, so guitar specification is using the guitar specification. Mandolin is using mandolin. Okay. So how do you think about this design?
So which class is extending which one? Instrument is extending instrument spec.
Extend?
Is that what is happening between? Is it? No, I should be something.
Oh, so
Guitar spec and
guitar.
Guitar spec and mandolin.
No, I'm not talking about the subclasses. I'm talking about the two abstract classes.
instrument specification.
How are they linked?
Okay, so two abstract class. One is instrument. The other one is instrument specification.
Yeah.
Both of them are abstract classes.
Yeah.
And instrument specification is part of instrument, like a guitar specification is part of guitar.
Yeah, but I wanted to know how they are linked.
Here.
Yeah, what in terms of the code, what
There
is
is an instance of the instrument spec inside the instrument class.
Okay.
I don't know if I'm making myself clear, but there are two abstract classes, right?
I actually
is
feel,
one
I mean,
extending is
if
one
you think
extending
in
the other?
implementation way, right, like if it's Java kind, I
Mhm.
don't think it can actually be an abstract class. It has to be an interface.
An interface.
Right?
Yeah,
Exactly.
I'm
That's
reaching the
what- that's-
interface
yeah.
later.
That's
Here.
what I was wondering.
Yeah.
So we cannot
It should
have
be an
objects.
it should be an interface. Yeah.
Yeah, let's forget about any specific programming language right now. For now, think about abstract classes. Okay, so right now the design is these two are abstract classes, and both of them have two subclasses, and the subclass is a guitar with guitar specification. It's a similar relation between instrument and instrument specification. Okay, so that's the design right now. That's the design right now. Right. Yep. So how do you think about this design? It makes sense, right? It's
It makes
understandable.
You can see how it makes it very extensible. If you wanted to add another instrument, you already have an abstract class to take care of.
Yeah. And if there is ever a new spec to add to each of the instruments, you can just put it in what the instrument spec and it'll work for all.
Can you
Yeah.
scroll back up for a second?
Yeah.
Yeah.
Yeah. Yeah.
Right. So it's maybe some good side of it. So you see anything you don't like?
It's, the only problem with this is that you have a ton of classes to.
The search should not be with the like search guitar spec, right?
Yeah. Yeah.
Oh yeah, yeah, yeah.
Why? That kind of hit the point I want to make.
Oh,
There. So see the search.
Is this really an instrument? Because, I mean,
Search instrument spec.
So, yeah, so you have to search.
because you don't
Well-
want to search for each different type, because then you're looking.
Yeah. So in this design, when you are doing search, you actually need a separate search for each design, right? No, for each type of instrument, because they are all different.
Well, in the instrument, can you have like a description name, and then that would be what you could search instead of having to have a guitar search, mandolin search?
So you're trying to find some generalization. You can generalize the information from all this.
Well, everything's going to have a name. Like, you can't have an
Yeah.
instrument that doesn't have a name.
Yeah, that's a name. But what do we want to search? If you remember the guitar specification, we search according to the maybe serial number, the price, okay, the number of strings of wood, top wood, different kind of wood, but not all the instruments have this
That's true.
attribute, the same attributes, right? Maybe some instruments they
Some
don't have
people
wood.
like Newegg or
They don't have
something,
string.
Like DRAM.
Assume it's a drum.
Yeah.
Can you search for a drum with a similar search function? No?
But what we have here, we have guitar, we have mandolin, those are instruments. So what if we create an instrument spec, just as we did in the case of guitar spec? There is an instrument.
There is one. See?
Oh, okay, there's one there.
See? The instrument spec.
Oh, okay.
Could you create like a general type search for just all the stuff that would
Yeah.
be shared, and then you have specific ones for that, so you don't have to
You can do that, but that's gonna be a compromise, right? you can't. That's limited. That's actually limited the functionality of your
You
search.
could do both, couldn't you? You could have a very specific search, and then you could also have kind of a general search, just so, because, you know, you could have a search by name, but then you have to have one for each type of guitar, you know? So you could have a search for what is shared, and then a search for what is specific.
Yeah,
for each type.
that's actually that could work. It kind of, but when will you search for like as a general? And under what circumstances
So
will the
this one's
user?
search by price. Hey, you know, I got $50, I wanna buy an instrument, what can I find, you know?
Yeah, that makes sense. Yeah, that makes sense.
Yeah.
Maybe we want to keep a search specification,
Yeah.
like search general as a general. Yeah. And however, if we do need to specify search for guitar, search for mandolin, it's gonna be a little bit tricky because we need a separate search function for each of them because we implement it differently. And right now we only have two: guitar, mandolin. If we like Rick is getting rich, he has a store that sell everything, hundreds of them. Rick has Amazon. Okay, what's gonna happen? Or do we need like millions of search function, something like that? Right?
No,
Yeah.
I thought that was just one search function. Yeah.
And within the instrument it should call, right, like based on, the instrument specification, based on that it should call the right class to search.
Okay, maybe in the future we have more than instrument. Then we have avant instrument.
Like accessories or something.
Yeah, a lot of
or
things.
the extra strap.
Yeah, so that just make it more complicated. Okay, more complicated. So that's maybe some disadvantage of this design. Okay, so we're using abstract classes. Maybe we override. Maybe get price, set price, specification, something like this. We override them a little bit. Okay. Yeah, maybe, but this is kind of, if we have to have a search function for every instrument, right? It kind of violates the rule there. Because when you are in the most ideal situation, when you're doing a change, add something, modify something, the most ideal situation is you only do that in one class, okay, without touching the other classes, right? But now if we add a drum, we will have a drum subclass and drum specification class, and here we also need to modify the inventory. Okay. So maybe there are some other ways that can help us with this. So let's see. Maybe what are the some of the other options there? Yeah, by using instrument specification, we might turn the add guitar into add instrument, but yeah, so that's a similar issue we were talking there. Well, we can use maybe add instrument, but they may have different constructor. Like we may have a search function for everything, but they may have different specification details there. So that's a problem there. That's a problem there. I'm gonna skip this code. Just remember what I said. The logic is there. Like if we add or search with that abstract class or abstract specification class, like instrument specification, instrument spec, that is abstract class. Okay, we can do this add with instrument spec. but here we need to distinguish if that's here, if specification is an instance of guitar specification, or it is a instance of mandolin specification. Then we do things differently because they have different constructors. Okay, and the search is similar. Right, we need a search for each of them. So that means when we add something there, we also need to change a lot of things in the inventory class. Okay, so that's not a loose coupling. We touch too many classes to make one change. Right, we want to avoid that. That's something we want to avoid. Yeah, we have to search method. Since it's abstract, you have to give either a guitar specification or mandolin specification to this search method. And this problem indicators we may have a design problem. Yep. Yep. There gotta be some way to let us touch only one thing to finish the change. So to improve it, important part is coming. Improve it. All right. Yeah. How do you think? Any idea? Well, forget about searching. Let's redo the design.
I know like in C++, you can do kind of like template functions, so it doesn't take it like a specific type of variable. So you might be able to do something like that, where when it's implemented, it can add its own variable to search for.
Implementable, yeah. So that's similar to interface idea,
Yeah.
right? Implement the interface. Yes. Actually, we're trying to see how can we use this interface, this thing. Okay. Everyone knows what is interface in Java? Yes.
Sounds like a template or a framework. for a
Right.
class
Yeah.
or
Sounds like something like a template, like a flyable interface. Okay. Well, flyable interface contain method called fly. Every class that implement flyable interface should have a fly function. Right. Should have a fly function. And well, in Java, you can only have one superclass, but you can implement several interfaces. Yeah, so you can be flyable, you can be movable, you can be what? Yeah,
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 you got it.
something like that. Yeah. So. Right. Well, let's see. Yeah. Why do we have? So interfaces there. So why do we have those interfaces there? Right. There got to be some reason. Well, today you.
Subclass choosing how it wants to implement that function.
Yeah. Today let's see. Why do we that class? Why do we have those interfaces? How the interfaces help us with the design? Okay. Okay, this is repeat information, like what it's supposed to do. OO principle, flexible. We make it loosely coupled. Yeah. So the first thing and second thing is still the same. Okay. Does the new search tool do what it's supposed to do? Yes. It finds guitar and mandolins. Have you used the solid OO principles? Yes, we use encapsulation, inheritance, aggregation. Like specification is a part of instrument. But it still takes a lot of work to add new instrument types. So how easy is it to reuse this application, to adapt changes? Is it doable? Is it loosely coupled? So from what we observed, it's a little bit hard because touching too many classes, touch too many points to make one modification. Yeah, so it's tightly connected. Everything is tightly connected. Yeah. Now Rick wants to sell bass guitars, banjos, dobros, and fiddles. How do I pronounce it? The last one?
Fiddles.
Fiddles. Yeah, fiddles. Just different instrument, okay. Yeah, so adding every one of them is gonna bring you a lot of trouble there. So you have to modify a lot of them and increase the possibility of making those bugs. Maybe you forget something in one of them. You have searched for banjos, but you do not have search for dobros. Possible. Right. So still the same thing. We have to make that change. We have to add 4 new instrument types, new classes for new classes, and for new specification classes objects, or adding new instrument and add those search method. Too much changes. Okay, we're reaching here. Better design. Yeah. So here's the important principle here. Identify the aspects of your application that vary and separate them from what stays the same. This means you identify the part that may change frequently, and you want to separate it as a separate individual part from the other part. Okay, so that is also the idea of encapsulation. Things that change frequently, we encapsulate them in one class, or we can call it one module. Maybe it's a combination of 2 classes, it's possible, but ideally 1 class. And the result is fewer unintended consequences from code changes. I mean, because we do not have all these tightly coupled classes, we only need to modify 1 class to finish it. Yeah, that's a principle, but how do we do that? Identify the aspect of application that varies. What is that? What does that mean? Identify the changes needed, right? So that could be adding new classes, adding new type is something may need change, right? Okay. So we kind of identify that. How can we separate that? How can we do that? So that is the idea of encapsulation. Yeah, we want it. We all know that. Yeah, we identify that. We encapsulate that. So things will be better. And for better design, our goal is separating the changes from what stays the same. Yeah, I'll give you another example later. But let's look at this book example. So here we introduce this interface. The principle here is we program to an interface, not an implementation. So an interface has the dual rule of defining behavior that applies to multiple types, and also being the preferred focus of classes that use those types. Okay, this sounds pretty theory, but we always like this example. So So this is the example. I see the duck here. We have a superclass called duck, which has the quack, swim, display, this kind of master there. And our ducks, quack, and swim, and the superclass take care of the implementation code. And the display method is abstract since all the duck subtype look different, right? Because they all swim. Yeah, okay. So I'm gonna implement that for you. Quack, okay, I'm implementing that for you. So you don't have to re-implement that. The only thing you want to do is the display, right? So the display, okay, that's something different. I'll let you to decide what you're gonna do, right? It's a little bit close to like encapsulate the change because only the change, the display is the thing that needs to be changed. It's kind of encapsulated, right? Yeah. Well, we took a step closer, yeah, but still we have a problem with this design. Can you tell? Think about more.
Yeah, if you have like a rubber duck, it doesn't really quack.
Yes, yes. When we have more and more ducks aided, rubber duck, it doesn't quack, or it quack kind of differently because you squeeze it, it quack differently, and it doesn't really swim, it just float there, right? So it's gonna be kind of different. That's the problem here. And I know, yeah, we know a duck may not fly, but now how about we wanted ducks to fly? If we wanted to fly, what can we do? This even no fly functions here in this duck, right? So okay, if at the meeting your boss decide we're gonna make a game that's called Flying Duck, all right, but you've already have 100 of ducks here. Implement this duck superclass, and every one of them have three functions: quack, swim, and display. But they do not have a fly function. So now what you do is you add a fly function to this duck superclass, maybe as an abstract function. There's nothing there. Okay, then we kind of make the duck flyable, right? But the problem with that is we only want one duck that can fly, one kind of duck that can fly. But every duck here, like red-head duck, okay, mallard duck, every duck here that inherited from the duck superclass needs to implement that fly function, needs to have a fly function, even though they are not flying at all, right? You have to have 100 more fly functions there to every class. That's a lot of modification. If you do it manually, you have to click every duck class doing that. Or yeah, maybe you have some a good IDE that can help you do some of this thing, but it doesn't make sense to make the duck that's not flyable to fly, to have a fly function. That's the problem of everything inherited from one superclass, right? See, a rubber duck will have this. Yeah, if we want to fly, when we really need to add fly for every, like flying rubber ducks, which doesn't make sense. So this is time when we are thinking about the interface, right? Here comes the interface. Why do we need interface? Okay, right now everything is inherited from the duck, right? Okay, we have a swim and we have display. Yeah, sounds good. And every one of them have a swim and display. And right now, if we want to implement a fly function for some of the duck, but not all of them, we just need one more flyable interface here, right? And then we made this two duck, red-head duck and mallard duck, to implement this flyable interface. All right. Then the fly function goes into these two specific kinds of ducks, but you do not find fly function in rubber duck, nor the decoy duck. Yeah, I don't even know what is a decoy duck. What is decoy duck?
Is it, we think the
Okay. Yeah. Okay. And also, we can yeah, we don't have, remember, you can see here the duck function. We remove the quack function, because maybe not all the duck that make the sound. So instead, we make it like quackable, and we make this, yeah, mallard, red-head, rubber duck implement the quackable function, so that they all have quack 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 functions, but this decoy duck doesn't have it. Right? So yeah, so we kind of separate it a little bit. Right? We have this interface. We only extend this fly function to those who implement the flyable function, or implement the flyable interface. And although they are all inherited from the duck superclass, but they can have different behaviors now, right? And we separate the fly, we separate the quack, and in the duck, yeah, if we think not all the maybe duck can swim, maybe we have another interface called swimmable. Because we have this word swimmable. Yeah, swimmable. Swimmable interface. Okay, something like, but you get the idea. Yeah. So interface. Yes. Right. Not all ducks can quack. Not all ducks can fly.
But if that fly function is common to both that mallard duck and the red-head duck, you would be repeating the code in both, right?
The fly function.
If it was the same function, right? You would have to repeat in those two.
Yeah.
Right. That's yeah. If it's interface, yeah, it's not implemented.
Yeah.
But interface really is like a framework or structure there to help with the polymorphism. Like if we know, if we want to do some operation with all the ducks that is flyable, then that flyable comes into usage. Yeah. But this fly function, they may kind of different from different
No,
ducks.
but even if it was the same, there's no way of, would there be a way of doing it without repeating the code? Because Java at least allows us to only extend one class, right?
Yeah, here in this design, yeah, if they're the same, you kind of need to, yeah, write it twice. Yes, correct. Yeah, so here we have the two interfaces, fly behavior and quack behavior, along with the corresponding classes that implement each concrete behavior. Yeah, okay. This is actually answer the question you just asked. So this, in this design, I said in this design, now you have to make it twice, okay? But if we improve this design by saying it's fly behavior and quack behavior, Okay. So let's fly. Suppose we have two ways to fly. One is a normal fly, fly with wings. Maybe another one is called fly with. What else can you fly with?
Rocket.
Yeah. Okay. Fly with rocket and fly no way. Right. Just means you cannot fly. Okay. Suppose we have all this implementation of fly with wings, fly no way. Okay. What's the difference here between this one and the previous one? Previous one is we have duck that directly implement the interface. Here we don't see the duck. Right. The only thing we see is the behavior, different behaviors. Fly, different kinds of quick. Squick, quack, mute. Don't quick. Okay, but that's a quick behavior. Okay, so we model the behavior as interface instead of the fly. Okay, so the flyable is actually already another step closer to a very good design. It separates all these functions. This flyable ducks, it have a group, and you don't have this duplicate function for every class of the duck. But here we're trying to move another step further. Okay, now instead of quickable flyable, we have a fly behavior and quick behavior, and we have some of the class that implement these behaviors. Okay, so but where are all the ducks? How can we make the ducks have this behavior?
They just have to implement the interface they need to implement.
No. Right now, the ducks do not implement the interface anymore. All these behaviors, they implement interface.
Oh, have an instance of dog in those.
And now, yeah. Suppose we want to start from here. Okay, we have behaviors now. Okay.
No, I thought those the behaviors, the implementations down there, they are implementing that interface.
Yeah, it implements this
But-
interface, but those are behaviors. Those
Yes,
are not
so-
ducks.
Yeah, so they are part of those the two behaviors, and so docs can implement any one of or both of the behaviors.
Duck doesn't implement behavior. Duck can implement all these interfaces. But interfaces has already been implemented by these behaviors, right? These are the classes. These three are the class. This is the
We
super
have
class.
instance of dog in those classes.
Yeah, so the
Yeah.
duck still has to implement the behavior, but it gets all that. For example, if a duck implements quack behavior, it can choose any one of the subclasses. Is that what it is?
No, that's not the case.
Okay.
If you implement a behavior, you have to implement the method of the behavior of the interface. Okay, but here.
If you take it as an attribute, maybe it will come in, right?
Yeah. So here the idea. Let me tell you the idea behind this design. Okay. Because we are trying to say these things constantly change. Not every duck can fly. We are eating a lot of ducks, but not every duck can fly. Not every duck can quack, and each duck they fly differently, and each duck they quack differently. So that's the difference there. Remember the principle. We want to remember the difference here is, the principle here is we want to separate the difference. Right now, we are separating the difference. We are separating the part that's constantly changed. Fly is the part that different from duck to duck. Quack is the part that differently from duck to duck. Right? Okay, so right now we separated. Okay, we successfully separated it. Now, but still, where are all the ducks? What if we want to put ducks back? How can we connect duck with this behavior?
You would have an abstract duck class that would implement all these interfaces.
So you'd have a method that would create like a new behavior, which would be that one that would call, and then we'll call that.
Yeah, very close actually. Okay, when we talk about interface, it's not like when we have an interface, the only thing we can do with the interface is implementation. No, interface can be a part of another thing. Interface can have has a relation as well, right? We can have a duck has a fly behavior. Duck has a quack behavior, right? So we can use that aggregation relation to connect the duck and the duck's behavior, right? Since we separate all these behaviors, we take it out from duck. We take the fly out from duck. We take the quack out from the duck. We make them an interface, and under each interface we have a whole bunch of different implementation of the interface. Okay, so behavior is one of the part. It's a part of the duck. Then the design actually will be. Don't we have it? All right. Now here it is. We have a duck, right? And we have a duck class, and the duck class have all these flying behaviors, have all this quacking behaviors. So every duck has a flying behavior. Every duck has a quack behavior. Okay, but to every of the duck, like each instance of the duck, whether it's a rubber duck, it's a red-head duck, how it fly and how it quack. See, we already have all this implementation here. Right? We can have a red-head duck fly with wings. Fly with wings is a part of red duck. Right? Maybe fly no way is a part of rubber duck. Okay, you understand me? So we can have this behavior as a part of the duck. So we actually first we separated all these behaviors from this duck, and if we want to aid a duck that flies with a rocket, we can have a class called fly with rocket, which implement the fly behavior, right? And then we have some machine duck that have a reference to fly with rocket, something like that. Okay, so and also we can have a rubber duck have a reference to this mute quack. Yeah, because of the rubber duck, red-head duck, they are duck. The duck has here, see here, duck has fly behavior. Duck has quack behavior. These two, they are interfaces. They're interfaces. So you can actually use like fly behavior. You can assign a value to fly behavior. You can assign quack behavior. You can assign mute quack. You can assign squawk to this quack behavior because or this three implementation, quack, squawk, and mute quack, they are all quack behavior. So that's polymorphism. Okay. So this reference of quack behavior is of the type quack behavior. It can hold the reference of any implementation of quack behavior. Okay. So that when you adding like more ways of quack, more ways of flying, what you need to do is you can just put one more implementation of this behavior, right? And when you add a new duck, you can just say my quack behavior equal mute quack. My quack behavior equal fly no way. It's okay, yeah. So then this is actually the design what we want. Yeah, okay, so this is more clear. See, here we have a duck class on the left side. It's a big one. It's a super class duck, and the duck has this flyable behavior. The duck has a quackable behavior, and flyable have 2 implementation. Quackable have 3 implementation. Okay, and the duck has different kind of duck: red hat, rubber duck, decoy duck, mallard duck. Look at the boxes. Okay, here we call it client because that's all the ducks. We call this ducks a client. That's what ducks we want. Maybe we want a different thing. Okay, those 2 boxes on the right side, it explains what is encapsulation. Right, that's encapsulated fly behavior, and the lower one is encapsulated quack behavior. We finish this kind of implement this kind of encapsulation with the interface, because we grab the quack out, put them as an interface, then we have different implementations here. So this way we're doing the encapsulation. We separate the changes from the duck. Okay, yeah, main idea behind this, we want to separate the change. And the tools we're using here is the interface. Okay. And remember, when you're talking about interface, it's not always implemented. Yeah, we do have classes that implement this interface. But pay attention to here, these two lines, from client to flyer behavior, from client to quack behavior. Okay, right now it's using some association, means we have reference to it. We can also use the aggregation, which is the has a relation. Okay, it's going to be similar. Like duck has a fly behavior, duck has a quack behavior. Interface can be a part of something else. Okay, we have this interface, which means we can use any implementation of this interface. Right. So this is encapsulation. So far so good? Any question regarding this? Yeah, I hope this is clear. Yeah, that's the magic here. We use the interface to separate changes. This is important. Yeah, so this is a text description of that diagram. So we're going to create 2 set of classes. Each set of class will hold all the implementation of their respective behavior. One set is given this description. What is this paragraph talking about? For the duck, we are going to create 2 set of classes. Each set of class will hold all the implementations of their respective behavior. What are the 2 sets? If you cannot answer this question, that means you are not paying attention to me.
You're going to create 2 sets of classes, the interfaces?
Yeah, right, the 2 interfaces. Quackable, flyable, 2 set. Quackable with its quackable interface with, no, not quackable, quack behavior with all these implementations. And fly behavior with all the implementations. Okay. Interface represents each behavior. Each implementation of a behavior will implement one of these interfaces. Yes. Yeah, a set of classes whose entire reason of living is to represent a behavior, and it's the behavior class. which implement the behavior. So these are all the behavior class. Fly with wings, fly with no way, fly no way. These are the behavior class. So that's the idea of using the interfaces, right? Right, compare with this duck and different implementation, override, this kind of thing. Compare with inheritance. How do you think the benefit of interface?
It's extendable.
What?
It's extendable.
Extendable. Why is extendable? It's because we separate the things that change, right? Quick, fly, these things. That is different from duck to duck. And if you want to add a new duck, you need to consider all this question if you do not have those behaviors.
Yeah.
But now if you add a duck, you just need to select a behavior or create a new implementation of the behavior. That's it. You add a new class, new duck class, maybe select one from the existing behaviors. That's only one new class to finish this 8. Or you add a new class, you find out it's not there. So at most it's 3 new classes. Right? But you do not have to touch the duck class or something above the duck, maybe an inventory of duck. You do not touch them at all. It's none of that business. Yeah. So
So dog is still a subclass, right?
actually, you know what? Here it doesn't mention that, but actually it doesn't matter now. It doesn't matter now. You can make it maybe part of them implemented, like some of the code is written. The other functions are abstract, or you can make it fully abstract. But that's not what we interested in now. What we're interested in is we separate changes. So here you can make abstract class. You can make a class that maybe with some override. It's maybe different from different situation. Okay. But if you do find that there's some method here like display. Like display, if you have some display here that is different from, well, display must be different from one from every duck looks kind of different. So you don't have to like, yeah, okay. Let me explain this way.
Display has to be overridden by the.
Okay. So if it's some change that is different with in all the ducks, like the display, everyone is different. Okay, so you can have a abstract display there in the superclass and implement them differently here. However, yeah, here the encapsulation. Here we're dealing with the situation that it's some of the duck, they are similar with the other group. So a group of duck is similar with the other group, but the other group is different. Like some of the duck can quack. Some of the duck squawk. Some of the duck quack no way. Robot duck, machine duck, maybe something like that. So yeah, it's not like if it's all of them are different, we may want to use the inheritance. Okay. But if not, we try this has a relation to encapsulate so that we can have some common behavior. Like maybe duck 1 and duck 2, they all quack. Right? For this kind of situation. Here. But here, whether it is abstract class or half abstract or fully abstract or fully implemented, they are all inheritance. inheritance means everyone here has to follow the thing in the superclass. But the value of interfaces is only some of them needs to follow one behavior. Some of them do not have to. Okay? Only duck2 and duck3 follow this quack. Not follow this quack, have this quack. Duck1 and 2, they are free to choose no quack. Okay. But with inheritance, things are less flexible. You have to have this function there. Yeah. So we'll have make a set of classes whose entire reason for okay, I read this part. Use interfaces, yes. So yeah, this is in contrast to the way we were doing, where a behavior either came from a concrete implementation in superclass or by a specialized implementation in the subclass. So they both rely on the implementation. So, okay, the whole first paragraph is telling you interface is in comparison with the inheritance. Okay, inheritance is a relation. The interface has a relation. Okay, actually, has a relation. Usually, it becomes more flexible than is a relation, because that actually fixes a lot of things. You have to have all this whole set, but has you can be things can vary. Okay, I believe you got this idea from the duck example. So what we do is subclass use a behavior represented by an interface, or has a behavior represented by interface, so that the actual implementation of the behavior won't be locked, won't be fixed. Okay, so you have the freedom to choose different behavior. So the key is delegate the behavior. Delegation has a delegation. And use has a, how can we use has a to encapsulate these changes? Yeah. And that is also the idea of the polymorphism for change behavior at runtime. Each duck object will set these variables polymorphically to reference the specific behavior type it would at runtime. Polymorphism, you all know what does it mean? The polymorphism? Yeah. Yes. That during runtime you can change, right? We can have a because we have I have a quack behavior. Right now maybe I'm sending to non-quack, but during runtime my quack behavior can change because all these behaviors they implement this interface. So as long as I have a reference to quack behavior, I can have not quack, I can have a quack, I can have a squack, or I can have a print quack, just output some print. So it can change, polymorphism. We are setting the behavior to concrete classes. We could easily change that, and a lot of flexibility here. Yeah, and setting the behavior dynamically to change behavior at runtime. Just call the setter method for that behavior. Yeah, so this is like can be better than is because what I mentioned has is more flexible. Because it's a composition, aggregation. instead of inheriting their behavior. The ducks get their behavior by being composed with the right component. So I mean, I have a placeholder for hand. Okay, I have a placeholder for hand. If I don't want this hand anymore, I can have a robot hand. I can have a machine installed here. That's a good thing about the composition, right? But right now, I inherited this hand from parents, so I cannot replace this hand. However, the sunglass here, right? That's a composition to me. I can easily change it. Yeah, as long as I have this interface to wear my sunglasses, right? Okay. We favor composition over inheritance because it's more flexible. And we're creating system using composition gives you a lot of more flexibility. Yeah, it encapsulate and let you change at runtime. Okay, we're almost done. What is change? Class, what is change? So each class should attempt to make sure that it has only one reason to do this, the death of many badly designed pieces of software. Okay, so that means we want to be very careful about the change, right? Because the change, once we change something, we fix a bug, we create 2 more bugs, or that's maybe a good situation. Sometimes we fix one, we have 10 of them. Yeah, so we design for this change, we separate this change. Yeah, and reduce the number of things in each class that can cause it to change. Reduce the number of things that can cause it to change. When we encapsulate the change, we don't need to touch the other classes. And avoid having classes trying to do too many things. Okay. Because there are some classes, there's some application there. Well, it's working. So the whole program has only one class which do everything. Okay, it may work, but the maintenance is horrible. It's gonna be horrible. Comparing with the beautiful design of this interface has a behavior. Yeah. So that's as a summary. What we learned today, encapsulate what varies. We put change together in one separate encapsulation. Like we're using interface. We're using a tool as interface. We're using a tool interface to help us with this encapsulation in object-oriented design. And we favor composition over inheritance. Yeah, everyone knows why. I repeat that again and again because composition is more flexible. Composition is more flexible. Think about the interface. We have that. Think about my interface. I have an interface for the sunglass. I can change it. I don't have an interface to replace my head. Okay, because that's inherited from my parents, right?
So how come in like some of the core principles of object-oriented programming, everyone says it's inheritance, but if we're going to favor composition over inheritance, why don't we just say when the principle should be composition then?
Okay, that means we favor composition over inheritance. That doesn't mean inheritance is nothing. It doesn't worth anything. It's, under some situation, we still need inheritance, right?
But why would we not say, a core principle would be composition, and then we can also say we have inheritance? Is it because inheritance is not... I'm saying, like, if we're going to favor composition, then in my mind, then composition is greater than inheritance. So then, why wouldn't composition be a core principle of OOD?
A core principle of OOD.
So, like, you're talking about.
Well, where do you find the core principle?
Yeah, but inheritance, capital, encapsulation, polymorphism. Those are the, what makes up object-oriented programming, right? But if we're going to favor composition over inheritance, then it seems like it's going to supersede it. So why would that not be a core principle then?
Okay, so yeah, I don't know the exact answer, but I guess for that core principles, core like inheritance, what's the other thing?
Polymorphism and encapsulation.
Yeah, encapsulation. Well, this object-oriented object-oriented principles they developed over a long time. Maybe that's something in the beginning we see this, but later we find out that maybe it's more complex, flexible. Composition is more flexible. So here we are standing on the perspective of being flexible. Okay. Okay, but maybe that's if we say that inheritance is a core value, maybe it's standing from the perspective of we're observing this overview of this object-oriented. Well, flexible is one thing, right? But there are some other things about object-oriented, right? Flexible is only one of them. But we want to be flexible. When we want to be flexible, we favor composition. Yeah. Okay, and okay, if we want something that less flexible, we just want every of my subclass to do it this way. I don't want any change. We want sometimes we want something that is fixed. We don't want to give the flexibility. Maybe that's inheritance, right? So, but here, flexible, we favor composition. And program to interfaces, not implementations. So that's basically 2 and 3 is the same thing. Composition, interfaces, and implementations. Yeah, inheritance. All right. So yeah, that's what we want to talk today. I hope you get the idea. Well, the core value here is the main principles here is this 3. All right, remember that, and remember the examples from this class, and think about it when you are doing the design for your maybe project or later future in your work. Okay. All right. Thank you very much.
So I have a quick question.
Yeah.
So how do we use these same principles to solve the problem we started with the guitar store?
Guitar store?
Yeah.
Yeah, think about it at home.
Okay.
We can talk about next time.